I'll speak today about field theory for that does two things. It generates a damage set or a fracture set as well as elastic deformation. So we create new boundary inside the domain as well as evaluate elastic fields outside that boundary. So that's the idea, and to have it as a well-posed initial value problem upon which then you can do analysis. So, maybe I'll have to be doing that. Anyway, this is work with, I'll talk about work with the Deep Bhattacharya and also work with Prashant Jha. So, as we all know, fracture is not a good thing. Try to avoid it or understand when it could happen, and so that's what we're after here today. Is a theory that it could possibly predict it. So what we'll do is we'll formulate it in terms of a non-local model, and then we can show how it localizes and recovers aspects of classic fracture theory, where you see a PDE, a time-varying PDE, outside a evolving internal boundary. And at the boundary, the elastic field is is traction free across the at the boundary. So this recovers sort of the scenario of classic fracture theory. So what we're after is a well-posed initial value problem for the displacement, and then we would like to see an energy balance between the energy of deformation and the energy that goes into creating new interfaces or internal boundaries. So we'd like to see an energy balance here that arises naturally without any hypotheses from the dynamics. So we simply take the equation of motion, multiply it by the velocity, integrate over the domain, and then find out whatever's going to happen. So we want it to be perfectly autonomous and deduce things from it, not postulate things a priori and say, but instead, write a boundary value problem, multiply, and see what quantities are conserved. What is interesting is that the failure energy, design this model, is such that it turns out to be a two-dimensional or a codimension one energy of sort of failure is it fails on surfaces, okay? And this is not postulated in the model or anything. It is designed so that happens, but it comes out of the modeling. So that's a thing. Again, it's not postulated, but it comes out, and it's engineered to come out. And there's a certain scaling, an energy scaling, such that the energy of the elastic motion is balanced by the energy that goes into creating new interface. That energy happens to be given by a measure supported on a deep dimension, a codimension 1 surface, and it is a property of the potentials used in this, okay? And we'll see this through the vehicle of geometric measure theory. And as a test, if the damage set turns out to be a flat crack, you get immediately the classic Griffith surface energy of fracture that was done in the 20s. And for more general rectifiable surfaces, if the crack happens to be a rectifiable surface, in the limit of vanishing nonlocality, where it becomes a local model, you recover the length of the crack again, multiplied by the Griffith fracture energy. So the idea here is that there are a lot of base points in which this theory edge cases of the theory touch, so to engender some confidence in the theory a little bit. Okay, so the last point is that all the energy balance and conservation laws follow multiplication of the velocity field by the equation, of evolution, and integrate by parts, and you get all this stuff. So no postulates. That's the key. So here's the body. So what we'd like to do, we'll do it in the non-local setting. And we're going to break things. Okay, so we wish to break things. And then we also have reversible elastic deformation. So those are the two things that we're doing. So we have our initial value problem here, which is basically that's the deformation. U is the deformation field. This is the second time derivative. This is the local density. This is the acceleration. This is a body force. And then this is the basically the interaction, the elastic and interaction and damage part is all contained in this term here. And the goal is then to complement things with initial conditions, the initial velocity being specified, the initial deformation being specified, and we'll have what is on the boundary of this set the natural boundary condition or traction, what amount to traction-free conditions in a non-local setting. And if you pass to the local setting in certain cases, you can show it's the usual traction force in h1/2 on the boundary. Okay. The length scale of non-locality will be denoted by epsilon, and so the goal here is to design a non-local operator so that we have a well-posed initial value problem as an ODE on a Banach space, and again, attain energy balance as a consequence of multiplying this equation of motion by the first time derivative of U everywhere and integrating over the body. So this is in the context, done in the context of what's called the paradigmatic formulation that Stuart Silling proposed in 2000. And it basically formulates evolution equation for the deformation, and when the strain between 2 points in the body becomes too big, you break. The range at which this strain, breaking means somehow the force between the 2 points goes to 0, and the range in which the force acts is confined. Say you have a point in the body, it interacts with a neighborhood of other points, and that diameter of that neighborhood is what's called epsilon. Okay. The nice thing about it is that paradigmatics breaks bonds as part of its evolution, of the time evolution of the deformation field. What is interesting and why it's still, it's become, popular is that defects and fractures appear, they emerge from the simulation. The problem is it's not a well-posed mathematical problem. However, it has been, set on a good course by the recent work of Chung Du, where you have damage, and Tian and I always forget the last author's name. I should. Tian and thank you. And then we've worked on this without the damage myself, and have gotten some gamma convergence and convergence in the limit of vanishing nonlocality to classic fracture theory. And it's also been shown to be well posed with damage by Emmerich and Pusht. Dmitry Pusht, did I say it correctly? And But the basic model or the idea, you know, breaking bonds, breaking things, and looking at deformation in a non-local way, it was proposed by Stuart Sill. Okay, and then it's been generalized to non-central force interactions. Okay, we're going to provide here a new perspective on the two-point interaction so that we can get energy balance by multiplying by the So the idea here is that we wish to couple, and this is going to be the new part, we wish to couple the displacement and damage evolution such that the coupling here and the scaling here, such that the multiplication of the evolution equation by the velocity and integration by parts gives you an energy balance from which then you can deduce a lot of things, okay? Like rules for when things should damage. They just pop out. Okay, one of the things that a priori pops out is that the energy expended to break bonds is supported on a d-1 dimensional set. Okay, so to describe the model, you look at a point x in the body, and you look at a nearby point within an epsilon neighborhood of x. And these 2 points can interact here, okay? And they're going to interact through the strain, and then the strain is going to be related to the force between these 2 points by a constitutive law, okay? Epsilon, again, will be the length scale of the non-local interaction, and the ball centered at x is written this way. So what we'll have here is we'll have the strain. So we have our deformation at time and position x, and the strain will be the difference in the deformation at the 2 points divided by how far away they are and resolved along the direction between the 2 points. Okay, so it's a very simple type of strain, but it's a strain that's in this difference coefficient formulation, if you look at the special functions of bounded deformation, this is the kind of strain that is very useful, SBD, special functions of bounded deformation, which is the sort of generalized notion of, it's a generalization of a Sobolev space where the derivatives of a deformation are given by Radon measures that have a regular part and a singular part with respect to Lebesgue measure. The singular part is the jump part. The regular part is basically the at L1 norm of the gradient. Okay. So when the horizon goes to 0, this is a very naturally converges to a strain in SB, or a deformation in SBD. So anyway, so we start with our strain here, and then the term that we're going to do here is what we're going to do is this is the force acting between x and y, and it will be a function of the strain, and it will be scaled appropriately. The square root y minus x times the strain, and the force on, this will be between x and y, the force between x and y will be given by a constitutive law related to the strain between x and y multiplied by this factor. Okay. Then this force will be pre-multiplied by this field which takes values between 0 and 1. When it's 0, the product here, of course, is 0, and that represents a failed bond. That is between x and y, we fail. Okay, when it's 1, this bond is in full strength. And the important part here that gives you this d-1 dimensional integral of the failure is because of this scaling here. So this scaling is such that the energies associated with elasticity can be compared with the energies associated with creation of new surface. So that's why that square root is there. Okay, that's the key. Okay, and this has been seen in other contexts by Michael Ortiz, and so you know, and it turns out if you then design these forces correctly, you can scale again like this and get a nice one-to-one relate apples and apples between a surface energy and an elastic energy. Okay. Now this here, this is a, you know, for every point x, y, and t, it's a number between 1 and 0, and this can be thought of as a phase field, if you will. And there's a popular fracture theory called phase field fracture theory, which many have heard of, and they couple this phase field to the force through what is called an Ambrosio-Tortorelli functional that maybe some of you have seen, which is basically Modica Mortola energy earlier on, but used to adapt it to damage in the fracture setting. And there, the Ambrosio-Tortorelli, they minimize energy. Here we're doing dynamics, we're not minimizing anything. So the currency of the problem really will be energy balance instead of minimization, energy minimization. So again, the force between 2 points, x and y, is this given by this constitutive law. So the force between x and y at time t is a function of the strain, x and y at time t, but rescaled. The bond between x and y is said to be broken when the force between x and y is 0. And again, this is harping on this 2-point phase field. State of the bond is 1, force is there. When that's 0, bond has been broken. So we have to build that in. So now the next thing is yeah, when does this all happen here? So what we do is we set our scaled strain to be just given by r here, and what we're going to do is this 0 to 1 object here will be given by a function, a composition of r star actually, where r star will be the maximum up. This is how the history gets into it. Up to time t, it will be the maximum strain. So we look at times before t, and we see, you know, in that interval where the max is, and that will be this rescaled strain. Here we are taking inspiration from the again composition introduced in Dew and Tao and 10 in Journal of Elasticity. We're just going to rescale it a little bit. Okay. The rescaling here is really important in the force function. You need it here too to be consistent. But so the degradation is coordinated with the bond force in the next slide. So we have to somehow coordinate degradation to the force. Okay. So now we get to the sort of a fuller expression. This row here is the localization. This is where x and y can influence each other. So you have a base point x, and it influences, you know, it can act with a force on points y within the neighborhood, and this j is the thing. This is the characteristic function, if you will, of the ball. And so it's 0 outside the ball and 1 in the ball. Or it can be a hat function, you know, spherical, or a cone. And then we divide by the volume of the ball, the epsilon, as well as, and this is important, adding this epsilon here. So adding the radius here to that, then we get our force, and of course then we have our scaling here, y minus x, square root, and here this is the y minus x square root times the strain in here, and here is what we call our potential function, g, the derivative of the potential function. And so we're going to design that g. That's the key here, in addition to the scaling, so that everything works. Okay, so now what we need to do to complete it is, as well, we need to coordinate the force and this phase field function. So so that they're coupled. And then we'll put it all together. Oh, I'm doing it this way, sorry. Okay, so here is the potential function, the force potential function, which we're going to look at here. It comes up and it goes down. So basically over here, this is negative, so R is this scaled strain, and so for positive pulling strains, you're initially linear elastic here, then you have a strength, and then you start to yield and go down to R plus, okay, to zero force. So G prime here will be giving us our force, and that's why I wrote this over here, G prime. So G prime is giving our force, and G prime will look like this. Now for strains that are pushing the material together, the force resists, the material resists being pushed together. So we have this going down like that, okay? And so this is the constitutive law right here. Now, this is just the antiderivative of it. This is just the antiderivative. And the area under this curve here is C plus. C plus. Now, the bond degradation is characterized exactly how it was done by Needleman, Falk, Needleman, and Rice in 2001 for the cohesive element model, okay? So we do it exactly the same way, okay? Which is, you allow the bond to soften, and that is an elastic thing, okay? And I hear you. Well, wait a minute. Well, should it be elastic? How do you... Well, we can do various variants of that, but because we're interested in fast fracture, like you crack and they're running and they're below the Rayleigh wave speed by half, but they're branching and they're running, this is a very nice way to capture it, okay? And this was done by Falk, Needleman, and Rice in 2001. It's also done by Martyr and Gross in their models. It's also done by Gao, Haojun Gao, in his modeling, in his atomistic modeling. And they get aspects of fracture. They get branching, they get the various nice things. Also, Xu and Needleman really took off with it, and they developed this. So anyway, so you basically, what we have, in some sense, can be thought of as a cohesive element model, but everything is cohesive elements now. Okay, so that's the idea. And so what happens is this. You go ahead, you elastically you get unstable here, you come down here, and you break right after here. You break right after here. And then you're broken, and you never heal after that. That's the history part. So once the force goes to zero here, between 2 points, it stays. Okay, the failure set is a collection of pairs, x and y, such that the bond between them was broken at some prior time, or it could be the current time. And the collection at time t of these bonds that have been broken is written by the gamma here, gamma epsilon, and the indicator function of this set gamma is on this product set, the product set of the domain, and it's 1 if it's broken, 0 otherwise. So now we have, well, I'll review then. So now we have designed we have designed our dynamic model. Now, we did put a lot in there, but the good thing is it's a well-posed ODE on a Banach space. So what we can then do, so we can show it's well-posed ODE on a Banach space, via Lipschitz continuity, it's sort of the standard ODE arguments, okay? So, okay, and we have uniqueness, so everything is good. Now, multiply that equation by the velocity, and write down the conservation law. So we integrate by parts using the fact we have a traction-free condition on the outer boundary, and we get initially, you see already, the derivative of the kinetic energy is appearing here, and then we have this full derivative now, because we integrate by parts. This then becomes a strain when we integrate by parts, and we ultimately get the time derivative of this, and this is the rescaled strain, and we have our kinetic energy, like I said. Then we could parse it out. We have our elastic energy. This is G, this is the phase field here. Then, as long as it's not zero, we have some elasticity there. The damage energy is given by the antiderivative of the derivative of the damage energy. And adding all together, the energies, we actually do get, from multiplying by the velocity of that equation, the energy balance. So now we have all that energies balanced. So this is the damage energy, this is there's an equality here. I could put that on the other side too. But I did it this way. So we have the damage energy, this is the energy put into the system up to time t. This is the kinetic energy, this is the elastic energy, this is the initial value. Maybe there's a crack system in there already. Okay, so those are the initial energies. Okay, so you can actually write the damage energy. There's a way you can rewrite the damage. You can move that outer time integral inside, integrate the derivative, and when you do that, you get 1 minus the phase field, and this is the damage energy. Okay, so the damage energy is increasing with time. The elastic energy is decreasing in time. Now it turns out, because of this rho, we had a 1 over epsilon, okay, and this, we also had a 1 over volume. So this is an energy density, and then multiplied by 1 over epsilon. So when I take a volume integral, but I have a length scale downstairs, I automatically have a d minus 1 dimensional object. So the question then is okay, so that's the damage energy. However, if I go and look at the elastic energy, I don't have that because of the scaling. I have a regular d-dimensional damage energy. So this is the essence here, and that's why we can compare them. So so we get this, and we write down, when gamma is 0, this is when it's failed, and it remembers it's failed, and that's it. So what about this set? What can we say about this set? Or the failure energy? The fun part is you can use a little bit of change of variable of integration, and you can rewrite the failure energy as this object here, which is very close to what is called Crofton's formula from geometric measure theory, and we can use that to calculate this failure energy. Okay, so what one did here was one uses slicing coordinates. One uses Fubini's theorem and slicing coordinates from geometric measure theory, and you can actually get this formula again. So we can do it the other way too. We can calculate f here, but it gets revealed much better when we start to use slicing coordinates. And the nice thing is we have a Grunwald inequality, we have dynamics, we have energy balance, we have a Grunwald inequality. shows that the damage energy is bounded by the external energy applied to the body. And for flat crack geometries, you know, when the broken bonds, you know, are all bonds across a line or a piece of plane are all broken. That is, the top point that cannot exert above the plane cannot exert any force below the plane, and vice versa. That's a crack. And flat crack geometries show, we can do a calculation, that this damage energy is non-negative, so it's not zero. Okay, so that's important. Since this is a surface kind of energy, and if F happened to be a volume quantity, then we would get zero, but F is not. You can calculate the energy required to make a point X not interact with any point Y above it within the horizon. You can calculate that, and then you can take points X and move it from right adjacent to the crack and move it down epsilon. And in calculating all of the energy it required to break those bonds, which you can do, you recover what is called the fracture toughness per unit length. Okay? And for the bond model treated here, calculus, it gives us this value. Whether we're in 3 dimensions, D is 3 or D is 2. We can do a plane stress, which is simply a symmetry of the body. We can appeal directly to Crofton's formula for this case of flat cracks. We get the failure energy is exactly GC. This is the fracture at critical energy release rate called GC, the amount it takes to make a fracture per unit length, times the length of the fracture set or the area of the fracture set. So this is the Hausdorff, this is Hausdorff Institute, and this is Hausdorff measure. This is exactly Hausdorff measure. So, or if you will, the special case of length and area. For kinked-in curve cracks, we have to pass to the limit of zero horizon, and when we do that, we then get, again, for kinked-in curve cracks, we also get the Griffith, this critical energy release rate multiplied by the Hausdorff measure of the length of the kinked or curved. But then we can go to fully rectifiable, and you use the full power of the Crofton's formula to get that as the horizon goes to zero, and we have a rectifiable set, then it's bounded, and we again have and this time it is Hausdorff measure, because it's not necessarily a nice little surface anymore. But it still has components, countable number of components in C1 manifolds. Okay. So anyway, the energy in the case of reasonable cracks, it gives you back a classic theory, classic values. So in quiescent regions, now here's the other thing, in regions that are not cracked, you get back elastic energy. Okay, you do not get surface energy anymore, you get elastic energy, and these translate into what are called Lemay moduli, or elastic moduli. And here's for a 2-dimensional case and a 3-dimensional. Now, I just said, I just looked at the failure energy and said, okay, it's reasonable if the cracks are reasonable. But now the question is okay, you have your model, you're breaking bonds. How is the crack supposed to know what to do? Right? And so the crack geometry is determined by the dynamics. So cracks grow at their tips. So it all happens at the tip of the crack growth. Okay? So like in the dendritic growth, whatnot, you can have these growth of the dendrites, and they tend to grow from their tips. Here, cracks grow from their tips. So you can write down from the energy balance, you write down the rate form of energy balance. And again, the rate, the damage energy rate is given by the rate of change of this phase field with time. And you basically get that at the crack tips is where you're converting elastic energy into damage energy and then permanently ossified in these cracks. I mean, it's not ossified, but just, it doesn't change once it's damaged. And so you do this where this quantity is positive. So this quantity, this is the rate, this here without this, is the rate balance, also obtained directly from the equations of motion, okay? And then you note that when damage energy is changing, it's exactly when this is non-negative, when this is positive, okay? And so this basically says that the rate of energy change is positive, and it has ramifications. It means that this difference is positive. And this is the energy supplied to the system, or the energy rate supplied to the system, minus the rate of kinetic energy, minus the rate of elastic energy. And when the rate supplied to the system is bigger than the kinetic and elastic rate, you have damage. So you make a deduction from energy balance. So one does not a priori do it. That's the important thing. You just do it and it falls out. So you can actually put it into words. If the rate of energy put into the system exceeds the material's capacity to generate kinetic and elastic energy through displacement and velocity, then damage and fracture occurs. Okay? The difference here is that previous paradigmatic models assume a binary choice, and here, the geometry and location of the process zone with bonds in various states of damage emerge from the dynamics. Well, notice I really haven't, this wasn't very hard. That's good. Then the total energy in the process zone, that is where you're creating the crack. So you can almost think of this theory as a microscope. You're looking into the process zone of a crack, as well as seeing the big picture as well. So this is much like that cohesive element model, where they were trying to model the process zone in order to see the ramifications, and they saw crack branching, and they would design these potentials so as to, they learned that if you were, let us say, rigid and then started to decay, you wouldn't see crack branching. But if you were more elastic and then decay, you would, okay? Okay, so what the point is that it offers possibly, I'm not saying, it offers a way to look into the process zone. Okay, so we can split up the damage into the process zone and the failure, where it's cracked, and then we can write our energy balance again, which is the total energy put into the system minus the kinetic plus the elastic and the initial. What is interesting here is that the failure is historical. It remembers what happened in the past. This is now. This is current. What is happening currently. So that's the interesting part. Okay. And so, for example, here's a schematic. A failure zone or a crack propagating from the left to the right. What is happening here is that the bonds X and Y, so this is a bond, let's say, that straddles, going from this point here to this point here, straddles that interior interface or interior boundary and is broken. Okay, there's no force interaction between x and y. And then if you're a point here, x, you're not at this point, you're not influenced by anybody down here. Okay, or actually, yeah. Okay, so that's the idea. That's the idea. Okay, you can calibrate the models. You can calibrate these potentials to elastic properties, strength properties, and energy required to make new interface. So that's that are readily available. On the other hand, I think there's, and as is elucidated by, you know, people in the cohesive element, as elucidated by them, you really want to design them so that you see the dynamic aspects of crack growth and the speed at which cracks propagate. So you want to get the geometry of a crack in space-time in 4 dimensions, or in 3 dimensions. So you have a surface, and you would like to see it evolve. You'd like to get the shape right at each time, but then you'd like to get the location of the crack front at desired time correct as well. So doing so will involve engineering the shape of the potential. Okay, if you're willing to play this type of game, yes. You can adjust the horizon. You could say, well, okay, well, which horizon should I take? I know it should be a lot smaller than the body I'm going to crack, but and then you can use dimensionless groups, and this is a famous dimensionless group, which basically is the penny motivated by the radius of curvature of the penny-shaped crack and what it takes to, and so, you know, letting epsilon be a proxy for the radius of curvature, you could say, oh, you know, so this is an old quantity there, but that's, you know, a choice that you could make. So here's some numerical simulations. So what we're doing here in this sample is we're pulling straight up, and we're pulling straight down here, and we're pulling with a constant force along the x-axis down, and a constant force along the x-axis up. The right-hand side and the left-hand sides are held traction-free, no forces there. And so we have a pre-crack that actually starts right around here. And then we pull hard enough, it begins to move. Okay, and so...
Sorry, can you repeat the boundary conditions again? So the top one, what's the boundary condition?
Yeah, the top one here is a force, it's a traction force pulling up. You're going to pull up.
Okay, and the bottom one down, or...
And the bottom one down.
Okay, and the other one?
It's very symmetric. And then on this side, we're traction free.
Okay.
We're not, no forces here, no forces here. Okay.
And the other one?
And all of them are going to be the same.
Both have the same boundary conditions. The top and the bottom. Sorry.
Yes. So it's very, and that's why we're seeing a crack right in the middle. It's very symmetric here. So and then we make a crack. We break bonds, you know, along a interior, you know, along a curve up to, let's say, here. Okay, and then we begin the evolution. We start pulling and pulling and pulling, and for a while nothing happens, and then. Yes, we have put enough energy into the system that this criterion with damage has been tripped, and we start to run. Of course, if we stop pulling, and then that criterion for damage stops, and the crack stops. Start, stop, start, stop.
So what is the color coding?
Pardon me?
What is the color coding?
Oh, this here is the displacement. So yellow is moving straight up, purple is moving straight down, green is kind of figuring it out. Yeah, it's the top part is talking to the bottom part, and in fact, the x deformation is actually even, and the y deformation is odd. It's an odd function. Okay. So what happens here is these are two panels, and what happens here is we pull faster. We pull faster. Okay, and this, what happens here too is we're later, this is a little later in the evolution. So each one of these is a little later in the evolution. So here's later. Now, but these two bottom things, I'm pulling at a faster rate. So here I pull, these are the same rate, and so the crack starts and it continues as one crack. Here I start to pull at a higher rate up and down, and the crack bifurcates. Then I'm going to just measure the strain concentration. You look at point X and you look at all your neighbors around them and you pick the maximum one, and that will be your scalar value that you associate with each point X. As you do that, you find that this is your crack here, this is your crack, this is your crack, and you find that your strain is largest at the tip, which you would hope. So because of that's really what's driving it. It's like a chain reaction. The strain is big, you crack to make the strain small. Just like a lightning rod. You look at the electrical field lines, a lightning rod, and they're bunched up. And when they get too bunched up, you'll get ionization of the gas, and you'll get a piece of lightning. This is very much similar. You have the option here to break. So this is, what we did in this model is in the constituent law, we gave it the option to break. We gave it a couple ways to deform. You can deform elastically or break. And if we pull harder, we get a crack, we get a bifurcation. We can then look at the strain energy density in the undamaged material, and that's what we do here. We look at the strain energy density, and we take values of it. And we find that the largest values of the strain energy density in an undamaged material is right in front of the crack. Okay, and that's true too when the crack splits. Okay, so strain energy density is being converted, elastic one, is being converted into surface energy. That's what's going on. We don't have a proof, that this, so there's a tantalizing thing that someone could prove. And so, but we see it numerically. This is also seen in the experiments of J. Feinberg and Bachbinder in PhysRev. So, we're recovering, we're seeing that. And then I could go on. I'll just be very fast and say, for this particular case, when the crack, it just runs in a straight line, you can actually go ahead and you can actually do weak convergence methods and get a PDE limit. So what we find is that we convert, the deformation converges strong. In this topology, the velocity converges weak. In this topology, and the acceleration converges weak in this topology, but it turns out the limit is in SBD. The jump set is contained inside the crack of this displacement. The U solves a wave equation outside the crack, and on the crack flanks, we have zero normal traction in the usual sense, as elements of H minus 1/2. And last, a simulation, a gratuitous simulation. So basically, again, we pull hard, and initially we start a crack to run. This crack doesn't exist yet. Then this crack runs in time, hits the sphere, or the void, and then you wait a while, you keep pulling, and then the crack comes out the other side there. And this is the displacement here. So thank you very much.